Welcome to Sleepy Stories. In this episode, we will explore how the universe quietly moves matter across the vast distances between stars, revealing a galaxy filled with travelers both small and immense. The purpose of this story is to help you learn while resting, allowing your mind to settle gently at its own pace. If sleep does not come right away, that is completely fine. You can let your breathing slow and allow the information to settle at its own pace. If you enjoy relaxing stories that help you wind down while understanding the world more clearly, feel free to like this video and subscribe to our channel for more calming explorations of science and nature. Now, as your body softens into comfort, we turn toward the silent journeys unfolding across the Milky Way. Interstellar space often appears empty from a distance, but in reality it contains a wide range of moving travelers. Atoms drift alone for thousands of years before meeting another particle. Dust grains formed in the cooling outflows of ancient stars travel slowly across regions shaped by starlight, turbulence, and magnetic fields. Larger fragments, such as icy bodies and rocky debris, wander between star systems, carrying chemical signatures from the environments where they formed. Some travelers are swift, moving at nearly the speed of light, while others drift so slowly that their motion becomes visible only across timescales far longer than a human lifetime. Yet all of them take part in a continuous exchange that links one corner of the galaxy to another. The distances involved are immense. Light itself takes years to travel from one star to its neighbor, and the Milky Way stretches across tens of thousands of light years. Despite this scale, matter does not remain confined to the region where it was created. Every particle is influenced by gravity, temperature differences, radiation, and magnetic patterns that extend across space. These forces shape subtle paths that guide material from its birthplace to new environments. A single carbon atom may drift through multiple clouds, star-forming regions, and diffuse zones before becoming part of a molecule. A dust grain may travel far from the star that formed it, before joining a cloud preparing to collapse into new generations of stars. Dust grains are particularly important travelers. They carry icy mantles that store water, methane, ammonia, and complex organic molecules formed in cold, dark regions. These mantles act as chemical archives, preserving information about the environments the grain has passed through. Over time, the grain becomes a layered record of interstellar conditions, from ultraviolet illuminated edges of clouds to quiet, shielded interiors. Turbulence stirs these grains, pushing them through pockets of varying temperature and density, allowing their chemistry to evolve gradually. Eventually, some grains gather in regions where gravity begins to dominate, contributing to the earliest stages of star formation. Larger travelers include bodies that once belonged to planetary systems. Comets can be nudged from their distant reservoirs and eventually escape the gravitational pull of their parent stars, drifting through space with their frozen interiors largely intact. Rogue planets, cast out during periods of instability in young systems, continue their journey through darkness, carrying the geological history of worlds that have lost their suns. Even these massive travelers obey the same quiet forces that guide dust grains. Gravity bends their paths slowly, magnetic structures influence any charged particles near them, and the overall rotation of the galaxy shapes their long-term motion. There are also travelers that move with astonishing speed. High-energy particles called cosmic rays cross the galaxy rapidly, propelled by supernova explosions or energetic magnetic structures. Photons, created in the cores of stars or in the glow of nebulae, journey outward for thousands of years before reaching distant regions. Neutrinos pass through nearly everything, revealing events deep within stars through their rare interactions. These fast travelers carry information rather than mass, allowing astronomers to study the farthest and most ancient processes in the cosmos. Even Earth is part of this circulation. The atoms that make up its oceans, its rocks, and every living thing once drifted across the galaxy. They came from stars that lived and died long before the solar system existed. They passed through cold regions, warm regions, turbulent regions, and calm expanses. When the cloud that became the sun began to collapse, these travelers gathered into what would become the planets. In this sense, Every person carries matter that once traveled far beyond the boundaries of the solar system. The galaxy is shaped by these quiet journeys. Turbulence mixes material into new patterns. Shockwaves from supernovae sculpt clouds and push particles into motion. Magnetic patterns stretch across enormous distances, guiding charged particles in spiraling paths. The rotation of the Milky Way creates broad circulations that draw material through spiral arms. Across all of these influences, matter continues to move, change, and return to new cycles of formation and dispersal. As you settle deeper into comfort, imagine these motions unfolding over long periods. Nothing rushes, nothing forces its path. Every traveler moves according to the quiet balance of forces around it, participating in a journey that has no beginning or end, but instead forms a continuous rhythm across cosmic time. That same sense of gentle movement can accompany your own rest now, as the story begins to travel deeper into the details of interstellar space. The space between stars may appear completely empty, yet it contains a delicate mixture of gas, dust, and magnetic structure that forms the environment through which countless travelers drift. This region is known as the interstellar medium. Although extraordinarily thin compared to any atmosphere on Earth, it holds the raw material for new stars and planets. In its quiet interior, hydrogen is the most abundant component, followed by helium and trace amounts of heavier elements. These atoms exist in different phases across the galaxy. Some regions are warm and ionized, others are cold and dense, and each phase shapes the motion of matter in distinct ways. Dust grains scattered throughout the interstellar medium add further complexity. They absorb starlight, cool their surroundings, and provide surfaces on which molecules can grow. In the warmer and more diffuse regions, atoms move freely. They collide infrequently, allowing them to drift across vast distances without significant interruption. Here, ultraviolet light from nearby stars can strip electrons from atoms, creating ionized pockets where magnetic forces have a stronger influence on motion. Charged particles respond to these fields by spiraling gently along their lines, tracing invisible arcs that stretch across light years. Although the density is low, these processes accumulate over immense timescales, imprinting subtle direction into the movement of interstellar matter. In colder regions, known as molecular clouds, conditions are very different. Gas becomes dense enough for molecules such as carbon monoxide and ammonia to form. Temperatures fall so low that dust grains accumulate icy mantles. These clouds are dark, quiet environments shielded from strong radiation. Matter moves slowly inside them because the low temperatures reduce the energy of atomic and molecular motion. Yet even here, the flow of gas is not still. Turbulence reaches into every scale, creating swirling currents that shift dust and molecules from one pocket to another. Gravity adds its own influence, pulling material inward when local densities rise. These competing forces shape a complex landscape where travelers follow paths determined by minute variations in pressure and movement. Transitions between these environments occur gradually. A dust grain drifting outward from a cold core may enter a slightly warmer region where molecules evaporate from its surface, releasing material into the surrounding gas. A molecule formed in the interior of a cloud may move into a diffuse zone where starlight breaks it apart, setting the stage for new reactions. Each environment contributes to the chemical and physical evolution of the matter passing through it. The interstellar medium acts not as a passive backdrop, but as an active participant in the galaxy's ongoing circulation. Starlight plays an important role in shaping motion within this medium. Photons exert gentle pressure on dust grains, gradually pushing them away from bright regions. Over long durations, this pressure can steer grains into new corridors of movement. These grains, in turn, influence their surroundings by absorbing energetic light and re-emitting it at infrared wavelengths, cooling the gas around them. Cooling promotes further molecular formation, especially in denser regions where dust is more abundant. Thus, the interaction between light and dust creates feedback loops that help define the boundaries and flows within the interstellar medium. Variations in temperature further influence how gas and dust move. Warm regions expand, creating outward flows that can carry material into neighboring zones. Cooler regions contract, drawing matter inward. These movements generate pressure gradients that guide the distribution of atoms and molecules. Although the forces involved are subtle, they persist for long enough to reshape entire clouds. Over millions of years, small shifts in motion accumulate into broad changes that alter the distribution of matter on galactic scales. Magnetic fields weave throughout this medium, though they cannot be seen directly. Their influence becomes visible when dust grains align with their direction, polarizing the light that passes through a cloud. Observations of this polarized light reveal intricate patterns. These patterns trace magnetic structures that guide charged particles and provide stability against gravitational collapse in certain regions. Dust grains moving along these magnetic pathways contribute to the slow shaping of clouds, adding structure to flows that might otherwise be chaotic. Even the most diffuse regions of the interstellar medium maintain a quiet interplay of forces that determines where matter travels. Gas pressure, radiation, turbulence, magnetic tension, and gravity blend into a long, unfolding rhythm. A particle may drift for 1,000 years before encountering a significant change, yet those gradual variations direct its movement as surely as strong winds guide motion on Earth. In these ways, the interstellar medium becomes the starting environment for countless journeys. Every traveler begins here, shaped by conditions that stretch across light years and unfold across deep time. Stars shape their surroundings through a steady release of particles and light. Even a star that appears calm from a distance sends out a continuous stream of charged particles that flow through space as a stellar wind. These particles begin their journey at the surface of the star, where high temperatures give them enough energy to escape its gravitational pull. Once in motion, they move outward, interacting with the surrounding gas and dust. The extent of this influence depends on the properties of the star. Hot, massive stars produce strong winds that carve large cavities into nearby clouds. Cooler stars release gentler flows that still shape their immediate surroundings across long periods. Regardless of intensity, every stellar wind becomes part of the broader circulation of matter through the galaxy. Light also plays a significant role in moving matter away from stars. Photons exert a small but persistent push on dust grains, nudging them outward. Although this force is slight for any individual grain, its effects accumulate across great distances. A dust grain exposed to strong starlight may travel significant lengths before being slowed by collisions or entering a shadowed region. As grains move, they carry with them icy layers and molecules that later become involved in the chemistry of new environments. The gradual outward drift of material driven by starlight contributes to a steady exchange between regions near stars and the wider interstellar medium. Some stars, particularly those nearing the ends of their lives, shed large amounts of material much more dramatically. When a star expands into a giant phase, its outer layers cool and thicken, becoming more susceptible to being carried away by radiation pressure and pulsations. These outflows enrich the surrounding space with heavy elements such as carbon and oxygen that were forged in the star's interior. Once released, these atoms and dust grains begin their long journeys outward, eventually mixing with material from other stars. The diversity of elements in the interstellar medium grows over time because of these processes, providing the ingredients for future molecular clouds and planetary systems. Massive stars contribute in an even more powerful way. Their intense radiation and strong winds push gas outward at high speeds, reshaping the structure of nearby clouds. These winds sweep up dust and molecules, compressing some areas while dispersing others. The resulting shells expand for thousands of years, carrying material to regions far from the star that produced them. Such shells often evolve into intricate networks of filaments and cavities. Within these structures, particles travel in patterns influenced by density, temperature, magnetic forces, and gravitational pull. The interplay of these factors creates unique pathways for different kinds of matter. These ongoing releases from stars form the foundation of the chemical and physical diversity present in the interstellar medium. As material spreads outward, it interacts with other flows shaped by turbulence, temperature differences, and magnetic patterns. Over millions of years, atoms and grains that began near one star may travel into regions forming new stars. In this way, the contributions of long-extinguished stars remain active components of the galaxy's evolution. Each traveler becomes part of cycles that extend far beyond the lifespan of any single star. The influence of stellar outflows does not end when the wind slows. Even after the driving star has aged further or collapsed, the material it released continues to move, blending with the environment through which it drifts. When astronomers study the distribution of elements and dust in the galaxy, they see patterns created by countless stellar winds across time. These patterns reflect differences in density, the presence of ionized regions, and the structure of magnetic fields. In areas where winds from several stars overlap, complex networks of motion arise. Material can become redirected, slowed, or accelerated depending on the conditions it encounters. Over distances measured in light years, the motion produced by stellar winds contributes to the broader shaping of interstellar clouds. Gas and dust gradually rearrange themselves, creating conditions favorable for the next generation of stars. The contributions from many stars combine to build an ever-evolving landscape. Within this landscape, individual particles continue their journeys through pathways formed by the cumulative action of light, motion, and gravity. Their movement adds to the quiet processes that define the character of the Milky Way. When a massive star ends its life in a supernova, the surrounding space changes in profound ways. The explosion sends shock waves outward at tremendous speeds, carrying material enriched with heavy elements produced during the star's final stages. These shock waves move through the interstellar medium, compressing gas and dust in their path. The compression can trigger new patterns of motion within nearby clouds, creating regions where density rises enough for molecules to form or for gravity to begin drawing material together. The shockwave itself expands over time, slowing as it interacts with the ambient gas, but even as it weakens, it continues to shape the structure of its environment. The material ejected by the explosion cools gradually, forming dust grains and complex molecules within the expanding debris. These grains begin as fragments only a fraction of a micrometer across, yet they carry within them the chemical signatures of the star that produced them. As the debris mixes with the surrounding medium, these grains become part of a larger flow that may travel far from the site of the explosion. Each one becomes a small archive of processes that took place in the heart of a massive star. Their motion depends on interactions with turbulence, magnetic fields, and pressure gradients that redirect them according to the conditions they encounter. The expanding shock wave influences the motion of material beyond the debris itself. Gas is swept into arcs and shells that continue moving long after the initial explosion has faded from view. Within these shells, matter flows along curved paths, shaped by density variations. Some regions become turbulent, while others remain relatively orderly. Dust grains caught in these flows may travel great distances before slowing down. Because of these interactions, the areas around old supernova remnants contain intricate patterns of motion that reflect the history of the explosion. Shockwaves also redistribute energy throughout the interstellar medium. The heating and compression they create alter the temperatures of nearby gas, allowing some regions to cool more efficiently once the shockwave has passed. Cooling promotes the formation of molecules, while heating can drive additional waves of turbulence. These cycles of heating and cooling reshape the medium continually. Over time, the processes initiated by a single supernova influence the chemistry and motion of matter across a region that may span dozens of light years. In some cases, shockwaves collide with pre-existing clouds, sculpting their edges into new formations. The outer layers of these clouds may be pushed inward, increasing their density. If conditions are right, these changes can begin the slow process that leads to the collapse of a cloud into new stars. Material that once drifted freely becomes part of a more concentrated structure. The particles gathered in these regions include atoms and grains that originated in multiple environments, each carrying a unique chemical history. The interactions between shockwaves and clouds thus play a vital role in redistributing material throughout the galaxy and preparing it for future stages of evolution. While the powerful effects of the initial explosion diminish over time, The flow established by the expanding material continues to affect the movement of neighboring gas. Even after millions of years, the remnants of supernovae influence the distribution and alignment of dust, the paths of charged particles, and the density patterns within surrounding regions. These long-lasting influences show that the journey of matter released by a supernova does not end once the visible spectacle fades. Instead, the motion produced by the event becomes part of the broader network of flows shaping the interstellar medium. Supernova activity also contributes to the diversity of the galaxy's chemical composition. Heavy elements produced in the explosion become incorporated into dust grains and molecules that drift outward. When they eventually join new clouds, these elements enrich the material available for the next generation of stars and planets. In this way, each explosion becomes a step in the ongoing cycle of stellar evolution. The travelers produced in these events carry pieces of ancient stars into environments where new ones will form. The galaxy contains many remnants of past supernovae, each contributing its own patterns of motion. Together, they shape the distribution of matter across large regions. Their influence extends far beyond the locations where the explosions occurred, demonstrating that even brief events can send travelers on journeys that last for millions of years, weaving their paths into the wider structure of the Milky Way. Supernova shockwaves are not the only forces that reshape the interstellar environment. Long after the most energetic phases of an explosion fade, slower but persistent currents of motion continue to influence the behavior of nearby gas and dust. These currents arise from the way pressure, temperature, and density gradually rebalance themselves across large regions. Wherever gas is slightly warmer, it expands outward. Wherever it is cooler, it contracts. These differences generate broad flows that carry material into new zones, blending the contributions of many older events. Within these flows, dust grains experience gentle but continuous movement. A grain drifting near the edge of a cooling shell may be drawn into a region where density is higher. Another grain may be pushed outward by gradual expansion. Because these motions act over immense timescales, the direction of travel is often subtle, yet the cumulative effect is significant. Over millions of years, even slight shifts in pressure guide grains from one filament to another, moving them into environments where chemistry and temperature vary. Each new region influences the grain's surface, altering the ice layers and molecules it carries. Gas responds to these changes in more fluid ways. Temperatures and densities determine how quickly atoms and molecules collide, bond, or break apart. When cooling gas flows into denser areas, molecules such as carbon monoxide form more readily. When warmer gas pushes outward, those molecules may break apart under ultraviolet light. These cycles of formation and destruction create a dynamic chemical landscape. Travelers moving through these zones encounter conditions that continually reshape their structure and composition. Magnetic fields add another dimension to these motions. Although invisible, they thread through the interstellar medium, gently redirecting charged particles along curved paths. Where magnetic lines converge, matter may collect into elongated structures. Where they spread apart, matter flows outward more easily. Dust grains carrying small electric charges respond to these patterns by drifting preferentially along certain routes. Over time, magnetic guidance helps organize the movement of particles within clouds, contributing to the shape and orientation of filaments. These combined processes create a slow choreography of motion. Gas streams toward cooler regions, dust grains drift along magnetic corridors, and molecules shift as radiation shapes their environment. From a human perspective, these changes occur on timescales far too long to observe directly. Yet over cosmic periods, they define the structure of the interstellar medium, guiding travelers into environments that will influence their next transformations. Eventually, some of this moving material reaches regions where gravity begins to play a stronger role. As certain pockets within clouds grow denser, gravitational attraction increases, drawing material inward. Flows produced by earlier events now feed these growing regions, supplying them with dust, grains, atoms, and molecules that originated far away. This gathering process continues quietly until enough material accumulates to initiate the earliest stages of collapse. At that point, a new generation of stars begins to form, shaped by all the movements that directed matter into the dense core. Even after these dense regions start to contract, material from the surrounding medium continues to flow inward. The patterns established by older shock waves, turbulence, magnetic tension, and temperature gradients all contribute to the direction and speed of this motion. In this way, the broader interstellar environment remains linked to the formation of new structures. The quiet journeys of countless travelers, guided by subtle forces, supply the building blocks for future stars and planets. The interstellar medium is therefore not a static backdrop, but a continuously shifting network of currents. Every particle's journey contributes to the evolving composition and structure of the galaxy. Matter, released by events long past, becomes part of new environments, carrying histories etched into its atomic and molecular form. Across these vast scales, the movement remains gentle and persistent, shaping the unfolding story of the Milky Way. As matter flows into regions where gravity grows stronger, the earliest outlines of new structures begin to appear within a cloud. These outlines are not visible in ordinary light, yet they shape the movements of dust and gas on scales far larger than any single traveler. Within these forming regions, gravity draws particles inward, creating narrow channels through which material steadily moves. Dust grains that once drifted freely now follow curved paths determined by the growing concentration of mass. Atoms and molecules respond as well, drifting toward the deepening center where density continues to rise. Surrounding these forming regions, turbulence adds variation to the inward flow. Some pockets of gas move more quickly, while others lag behind. These differences create a textured pattern of motion. A dust grain passing through may weave between currents before settling into a slower inward drift. The grain's temperature changes as it approaches denser material. Warmer zones near the edges allow some molecules to escape from its icy surface. Cooler areas deeper inside encourage new layers of ice to form. In this way, even during the early stages of collapse, the chemistry of a grain evolves in response to its environment. Magnetic fields influence these motions by channeling charged particles along aligned paths. Where magnetic tension is high, gas may resist collapse, creating elongated structures that slow the inward motion. In regions where the field is weaker or more distorted, material flows inward more freely. Dust grains feel less of this influence unless they carry electric charge, yet they still respond indirectly through their interactions with the moving gas. The combined effect produces a gradual organization of matter into flattened, rotating forms. As the central concentration grows, rotation begins to play a more significant role. Even a slight initial spin becomes more pronounced as material falls inward. Conservation of angular momentum causes the rotating region to flatten into a broad disk. This transformation marks a major shift in the movement of interstellar travelers. Instead of drifting randomly through three-dimensional space, many now follow circular or elliptical paths within the forming disk. Dust grains collide gently, sometimes sticking together in pairs or small clusters. Molecules evaporate from grains in warmer inner regions and refreeze farther out, redistributing chemistry across the disk. Within this rotating environment, temperature gradients appear. The inner regions become warmer due to the growing central mass, while the outer areas remain cold. These gradients determine where certain molecules can remain stable. Water ice survives only in cooler zones, while volatile substances such as carbon monoxide evaporate near the center. As dust grains move through these regions, their composition shifts. Some lose their icy layers entirely, others accumulate new materials. These differences contribute to the diversity seen later in forming planets, comets, and smaller bodies. Localized concentrations of matter develop within the disk, as dust grains collide repeatedly. Over time, these collisions produce larger particles capable of influencing their surroundings. Such particles may stir nearby gas, creating small patterns of motion that feed back into their own growth. Even at this early stage, the properties of individual travelers begin shaping the environment from which new structures will emerge. The disk becomes a place where interstellar histories meet. Dust grains with varied origins blend their chemistry as they move along shared paths. Farther from the center, motion remains slower and colder. In these distant regions, dust and gas continue to drift in gentle patterns influenced by the outer portions of the magnetic field and the broader cloud. Though the gravitational pull is weaker here, it still guides travelers into long, looping orbits that gradually bring them toward the more active interior. Every particle moving through these outer regions contributes to the overall growth of the system, even if its path remains relatively calm. Across all these processes, movement remains the defining feature. Flowing gas, drifting dust, rotating disks, and accumulating bodies form a continuous sequence, linking the earliest motions of interstellar matter to the beginnings of new stars and planetary systems. Each traveler plays a part in shaping the next stage of development, carrying with it a story that began long before the cloud itself started to collapse. As the rotating disk surrounding the young central mass continues to evolve, the movement of gas and dust grows increasingly organized. What was once a loose collection of drifting particles now follows patterns shaped by temperature, pressure, and rotation. These patterns guide material into curved paths that gradually define the structure of the disk. Dust grains, once influenced mainly by random collisions and distant turbulence, now feel the steady pull of orbital motion. Their trajectories become smoother as they settle into the plane where most of the mass resides. The gas within the disk behaves differently from the solid grains. Because it experiences pressure forces, it can move in spirals, flowing slowly inward while maintaining a rotating pattern. This inward drift affects the distribution of dust. Grains collide with gas molecules, losing a small amount of momentum with each interaction. Over time, this causes larger particles to drift toward the central regions. Smaller grains remain suspended for longer, carried by slight variations in gas flow. These differences allow distinct types of material to collect in different zones, laying groundwork for the diversity seen later in planetary systems. As material moves inward, heat becomes increasingly important. The rising temperature changes how molecules behave. Some substances that remain stable as ices in the outer regions evaporate as they approach the warmer interior. When these gases move outward again through turbulent eddies, they may cool and refreeze onto dust grains. This cycle of evaporation and condensation acts as a form of chemical sorting. Molecules with higher volatility remain in motion longer, while less volatile substances stay locked onto solids. In this way, the inner and outer parts of the disk begin to acquire distinct chemical identities. Collisions among dust grains grow more significant as densities increase. In the early stages, these collisions are gentle enough to allow grains to stick together. Over long periods, these attachments produce clusters large enough to feel their own interactions with the surrounding gas. Such clusters drift differently from single grains, moving more efficiently through the disk. As they encounter other clusters, further growth becomes possible. This gradual accumulation marks the earliest steps toward building larger solid bodies. Meanwhile, the outer regions of the disk remain calm compared to the warm, active interior. There, cool temperatures preserve delicate icy mantles that carry layered chemistry from earlier environments. These grains move slowly, following wide arcs defined by the disk's rotation and the faint pull of gravity from the forming central object. Their motion is steady, allowing them to pass repeatedly through regions where conditions change only slightly. These stable cycles become important for maintaining icy compounds that later influence the surface chemistry of forming comets and distant planetary bodies. Gas pressure continues to shape the overall flow. In some areas, pressure gradients cause the gas to move slightly faster than the orbiting solids. In others, it lags behind. These differences create zones where dust grains concentrate. Even small concentrations can lead to further accumulation, because local increases in density allow particles to collide more often. Over time, this process builds subtle structures across the disk, forming faint rings or clumps where material gathers. Although these early formations are not yet solid worlds, they represent the first signs of the patterns that will eventually dominate the system. Throughout these processes, the movement of material remains gentle but persistent. Grains drift inward, outward, and around the disk, following paths shaped by evolving forces. gas flows between warm and cool zones, carrying molecules that continually break apart and reform. Clusters of solid material grow slowly, influencing their surroundings in ways that feed back into their own development. Across millions of years, these quiet shifts guide the transformation of interstellar travelers from freely drifting particles into structured components of a newborn system. Turbulence fills much of the interstellar medium with motion that appears chaotic at first glance, but follows patterns shaped by energy flowing across many scales. In regions where supernova shockwaves have passed or where stellar winds have stirred the gas, eddies form that can span light years. These eddies twist and fold material, creating paths that a dust, grain, or molecule may follow for long periods before drifting into a calmer zone. Even in quieter regions, turbulence persists through small variations in temperature and pressure. These variations generate motion that blends material from different regions and allows chemistry to spread far beyond its point of origin. Gas responds to turbulence through continual reshaping. Dense pockets may form temporarily as motions converge, only to disperse again as currents shift. Molecules move with the gas, sometimes entering warmer layers where they break apart, then flowing back into cooler regions where they form again. The constant reformation of molecules creates a dynamic environment in which chemistry evolves gradually. Dust grains drift within this changing atmosphere, colliding occasionally with gas molecules and other grains. Each collision contributes to slight adjustments in motion, and each adjustment guides the grain toward new regions where conditions differ. Magnetic fields thread through these turbulent zones, adding another layer of complexity. Charged particles follow the curved lines of the magnetic field, but turbulence distorts these lines and causes them to twist and stretch. A particle moving through this environment spirals along a path that changes direction repeatedly. Dust grains that carry even a small electric charge feel these influences too. Their motion becomes a mixture of drifting, spiraling, and gentle redirection. Because the magnetic field extends across large stretches of the interstellar medium, this shaping of motion affects particles over enormous distances. Energy cascades through turbulence from large scales to small ones. A wave created by a distant stellar wind may begin as a broad movement that eventually fractures into many smaller movements. These smaller motions shape individual particles, pushing them into paths that intersect with regions of varying density and chemical activity. The smallest eddies influence how molecules collide and bond, contributing to the diversity of chemistry observed in molecular clouds. Over long durations, these repeated interactions enrich the medium with a variety of molecules formed in different conditions. The presence of turbulence also prevents the interstellar medium from becoming uniform. In regions shaped by strong turbulence, density differences remain pronounced. Some pockets contain dense clusters of molecules, while nearby areas remain thin. These variations influence later stages of star formation by determining where gravity can begin drawing material inward. Turbulence may delay collapse in some regions while encouraging it in others through local compression. Its dual role creates a landscape in constant motion, where calm and activity blend into a single evolving structure. Travelers moving through this environment experience a journey shaped not by straight lines but by long, wandering paths. A molecule may drift through calm regions before entering a turbulent zone that sends it into looping spirals. A dust grain may follow a slow trajectory for centuries before a shift in magnetic structure redirects it. Over time, these unpredictable movements spread material widely, ensuring that chemistry developed in one corner of the galaxy can reach another. The interstellar medium becomes a place of mixing and redistribution, where turbulence acts as the engine driving the exchange. Through these processes, turbulence influences not only the motion of matter but also the composition of regions where new stars and planets eventually form. The materials drawn into forming clouds have histories shaped by many cycles of disruption and settling. Their paths through turbulence contribute to the diversity of worlds that arise from these clouds. The travelers that pass through these shifting currents carry with them records of environments far from where they will eventually come to rest. Not all travelers move slowly through the interstellar medium. Some carry extraordinary amounts of energy and cross vast distances far more quickly than drifting dust grains or molecules. These are cosmic rays, particles accelerated to remarkable speeds by violent events such as supernova explosions or strong magnetic structures. Many of these particles are simple protons, while others are helium nuclei or heavier ions. Their speed allows them to travel great distances without being significantly slowed by the thin gas around them. Cosmic rays originate in environments where energy is released abruptly. A supernova shockwave can accelerate particles outward, sending them into space with velocities approaching the speed of light. Once free, these particles move in long arcs, shaped by magnetic fields that stretch across the galaxy. Although these arcs appear random when viewed on small scales, they follow patterns influenced by the overall magnetic structure of the Milky Way. As cosmic rays travel, they rarely collide with other particles because the density of the interstellar medium is extremely low. This allows them to maintain high speeds for vast periods. When cosmic rays do meet atoms or molecules, the collisions can produce significant effects. A single impact can ionize a molecule or break it apart, initiating chemical reactions that would not occur in darkness alone. These reactions contribute to the overall chemistry of molecular clouds by reshaping certain compounds. Even though cosmic rays are far less abundant than photons, their ability to penetrate deep into clouds makes them important drivers of chemistry in regions shielded from light. Dust grains, too, are affected. Repeated impacts alter surface structures, changing how molecules adhere or detach. Magnetic fields guide the paths of cosmic rays in subtle ways. Charged particles respond to magnetic forces by spiraling along the field lines, but turbulent distortions in the field cause these spirals to bend and twist. As a result, the journey of a cosmic ray becomes an intricate pathway with many changes in direction. Despite these changes, the particles continue to move outward, eventually crossing distances that span thousands of light years. The influence of magnetic patterns ensures that cosmic rays arrive from all directions, creating a diffuse flow that permeates many regions of the galaxy. Some cosmic rays originate from sources outside the Milky Way, traveling for millions of years before entering our galaxy. These particles carry information about environments far beyond the reach of most astronomical observations. When they are detected near the solar system, their energy levels and composition provide clues about the events that accelerated them. Although these particles cannot be traced back to precise locations because of the way magnetic fields bend their paths, their existence shows that high-energy processes shape not only our galaxy but others as well. Cosmic rays also interact with dust and gas in ways that influence the larger structure of the interstellar medium. Their passage contributes to maintaining a level of ionization in certain regions, which affects how gas behaves under the influence of magnetic fields. A slightly higher degree of ionization allows magnetic forces to couple more strongly with the gas, shaping flows and altering how material collapses into clouds. Over long timescales, these interactions help determine which regions of the galaxy remain diffuse and which evolve into dense molecular environments. Despite the energy they carry, cosmic rays do not dominate the movement of most interstellar matter. Their role is more subtle. They sculpt chemical pathways, influence magnetic interactions, and serve as indicators of energetic events scattered across the galaxy. While dust grains travel slowly and molecules drift quietly, cosmic rays cross these same spaces with speed and intensity, leaving faint signatures in their wake. Together, these different forms of motion contribute to the wider tapestry of interstellar travel, each shaping the galaxy in a unique way. Across many star-forming regions, long and narrow structures appear within clouds of gas and dust. These structures, known as filaments, act as natural pathways that guide the movement of matter through space. A filament may stretch for dozens of light years, forming a thread-like shape that contains denser material than the surrounding regions. Within these extended channels, dust grains and molecules move in more coordinated ways than in the broader interstellar medium. Their paths follow the gentle flow of gas drawn along the filament's length. Filaments form through a combination of gravity, turbulence, and magnetic influence. When turbulent currents compress gas in elongated patterns, density increases along narrow corridors. Gravity then strengthens these patterns by pulling more material inward, reinforcing the shape. Magnetic fields help maintain the structure by providing support along its length, preventing the filament from collapsing too quickly. Together, these forces create a stable channel where matter accumulates and follows predictable motions over long periods. Inside, a filament, temperature, and density vary gradually along its length. Some areas contain cooler gas where molecules bind readily to dust grains. Other areas are warmer, promoting evaporation or chemical change. A dust grain drifting through the filament experiences these shifts slowly, collecting or losing molecular layers depending on the local conditions. These subtle changes in chemistry contribute to the diversity of ice mantles and organic compounds found throughout the galaxy. The movement of gas within a filament is shaped by pressure differences. Material flows from slightly warmer regions toward cooler, denser ones. Over long timescales, these flows guide matter into central zones, where gravity begins to take over. These central zones may eventually form dense cores, the earliest seeds of new stars. Even before such cores develop, the presence of a filament influences how gas and dust travel through the cloud. Rather than drifting aimlessly, particles follow the elongated form, moving in smooth, extended paths. Filaments also act as boundaries within interstellar clouds. On one side, the gas may be diffuse and warm, shaped by nearby radiation. On the other side, it may be cold and shielded, containing molecules that would not survive closer to bright stars. A dust grain crossing from one side to the other experiences these differences gradually. In warm zones, ices may evaporate. In cold zones, they may reform, binding new molecules to the grain's surface. These transitions create complex chemical histories that remain encoded in the grain's layers. Although filaments appear quiet, they are not static. Turbulence continues to influence their structure, shifting density patterns and altering the flow of material. Magnetic fields may strengthen in some areas and weaken in others, changing how gas aligns along the filament's axis. Gravity acts slowly, drawing material inward and encouraging the development of dense cores. Each of these processes contributes to an evolving environment where travelers move in ways that reflect both stability and change. When observers study star-forming regions, they often find that young stars appear lined along the lengths of filaments. This pattern highlights the importance of these structures in guiding where collapse occurs. The dust and gas that once drifted freely now follow pathways shaped by earlier motions, making filaments essential components of the galaxy's long cycle of matter. They gather travelers from wide regions and direct them into zones where new generations of stars begin their development. Filaments, therefore, serve as bridges between the diffuse interstellar medium and the more concentrated environments that lead to star birth. The motion of travelers through these channels reflects millions of years of shaping by turbulence, gravity, and magnetic structure. Within these long corridors, the paths of countless particles begin to converge, setting the stage for the transformations that will occur deeper within the cloud. Tiny dust grains travel through the galaxy for extraordinary lengths of time, carrying with them records of the environments they have passed through. These grains form in several places. Some emerge from the cooling layers surrounding aging stars where temperatures fall enough for atoms to bond into solid structures. Others arise from the debris of supernovae as the expanding material cools and condenses. Still others grow within dense molecular clouds when atoms settle onto existing grains and gradually build new layers. Each grain begins its life with a unique composition shaped by the region in which it formed. Once released into the interstellar medium, dust grains drift according to the forces surrounding them. Turbulence nudges them into looping or wandering paths. Radiation pressure pushes them gently away from bright stars. Electrically charged grains respond to magnetic fields that thread through the gas, aligning their motion with the unseen structure. Gravitational pull from dense clouds or nearby stars can alter their direction, adding another influence to their journey. Because these forces act slowly, the grain's path becomes a reflection of the cumulative effects of many environments rather than a single event. As dust grains move, they collect layers of ice in cold regions where temperatures fall low enough for molecules to freeze. Water, methane, ammonia, and carbon monoxide form icy shells that coat the grain's surface. These layers often accumulate gradually, one atop another. Each layer carries the chemical imprint of the conditions that produced it, creating a long record of temperature, radiation, and local chemistry. When a grain encounters a warmer region, some of these layers may evaporate, releasing molecules back into the gas. Others remain intact, protected beneath additional layers that isolate them from changing conditions. Collisions between dust grains occur occasionally. Although the interstellar medium is extremely thin, grains traveling through turbulent or collapsing regions may encounter one another. Gentle impacts allow grains to stick together, forming slightly larger particles. More energetic collisions can fracture a grain into smaller pieces. Both outcomes contribute to the diversity of sizes found throughout the galaxy. Larger particles tend to drift differently, responding more strongly to gravitational forces and less to small-scale turbulence. Smaller fragments, on the other hand, remain more easily influenced by radiation and gas flow. Dust grains play a significant role in shaping interstellar chemistry. Their surfaces provide places where atoms can meet and form molecules that would not easily bind in free space. Hydrogen atoms, for example, can attach to a grain's surface and combine into molecular hydrogen before drifting away. More complex molecules form through similar processes, gradually building material that contributes to the chemistry of molecular clouds. These reactions depend on the grain's temperature, structure, and accumulated layers, all of which change during its travels. Over long durations, dust grains travel into environments where gravity begins to dominate. When they enter regions dense enough for collapse to start, they become part of the material gathering into protostars and disks. During this stage, their accumulated chemistry becomes important. The icy mantles they carry release molecules into warmer regions, influencing the gas composition near the forming star. Grains that survive intact become part of the solid material that later builds larger bodies. The journey of a single dust grain may span millions of years and cross many light years. Its experiences shape not only its own chemistry but also the environments into which it eventually settles. Whether it becomes part of a new star, a forming planet, or continues drifting through space, the grain remains an enduring traveler, carrying with it a record of the galaxy's long and gentle motions. Some of the most remarkable travelers in the galaxy are interstellar comets. These icy bodies begin in distant planetary systems, far from the warmth of their parent stars. For long periods, they orbit in calm, remote reservoirs where gravity holds them in wide, slow paths. A passing star or a gradual shift in the gravitational balance of the system can disturb these orbits. When the disturbance is strong enough, the comet moves outward on a path that eventually frees it from its star's influence. Once released, it becomes a traveler between the stars, drifting through regions where the light of any sun is faint and the surrounding gas is extremely thin. The structure of an interstellar comet tells a long story. Its outer layers bear the marks of radiation that has slowly altered molecules on its surface. Beneath these layers, deep ice preserves material from the environment where the comet formed. That material includes frozen water, carbon dioxide, methane, and traces of more complex molecules. Because these ices remain protected within the comet's interior, they store information about temperatures, pressures, and chemical processes from a time and place the comet has long since left behind. When such a comet approaches a new star, even briefly, the warmth releases some of these preserved substances, allowing observers to glimpse chemistry from a distant system. The motion of an interstellar comet is shaped by gravity and its own momentum. It travels in a broad curve determined by the positions of nearby stars. If it passes close enough to a star, its trajectory may change significantly. It might accelerate, slow, or alter direction slightly. Yet most of the time, the comet moves steadily, guided by forces that act over large distances. Radiation from stars can warm its surface slightly, causing small jets of gas to escape. These jets exert tiny forces that can adjust the comet's path, though the effects accumulate slowly. Interstellar comets experience environments that change gradually as they travel. In colder regions, ices remain stable. In slightly warmer zones, molecules on the surface may evaporate, thinning the outer layers. In areas with stronger radiation, the surface darkens as complex molecules form. These changes shape the appearance of the comet and influence how it interacts with light and heat. Dust grains released from its surface join the interstellar medium, becoming travelers in their own right. When observers detect an interstellar comet passing through the solar system, they witness only a brief portion of its long journey. Its speed and unusual path reveal that it does not belong to our Sun. The shape and behavior of the object provide clues about its origin. Some may come from regions rich in heavy elements. Others may reflect colder environments where different ice is formed. Each one carries information about the diversity of planetary systems in the galaxy. Their brief visits remind us that stars do not exist in isolation. Material moves freely between systems, linking them through the slow exchange of dust, gas, and icy fragments. A gentle parallel exists here between the slow journey of such a comet and the gradual settling of the mind toward rest. Just as the comet drifts without urgency, moving through calm and open space, your thoughts can drift without pressure. There is no need to reach stillness immediately. A quiet settling can unfold naturally, the way a traveler glides through the dark, untouched spaces between stars. These comets continue onward long after they leave any star's vicinity. Some may wander the galaxy for its entire lifetime. Others may eventually pass near another forming system, delivering their ancient chemistry to new environments. Their journeys show that even solitary travelers contribute to the long cycle of matter that shapes the Milky Way. Among the largest solitary travelers in the galaxy are rogue planets, worlds that no longer orbit a star. These planets begin like any others, forming within the disks that surround young stars. During the early stages of planetary development, gravitational interactions between forming planets can become intense. A close approach between two large bodies may transfer momentum in such a way that one of them is pushed outward. If this outward motion exceeds the gravitational pull of the star, the planet escapes into interstellar space. Encounters with passing stars can have similar results, especially in crowded regions where young stars form close together. Once released, the planet begins a journey through cold and distant expanses. A rogue planet experiences a far different environment than a planet bound to a star. Without a source of steady light or heat, its surface becomes extremely cold. Any atmosphere it once had may freeze and fall to the surface in layers of ice. Despite these conditions, the planet may still retain internal warmth. Radioactive elements within its core release heat slowly, and residual energy from its formation remains trapped deep inside. In some cases, this internal heat may sustain a subsurface ocean beneath thick layers of ice. The planet becomes a world of darkness, yet still carries active processes beneath its frozen surface. The motion of a rogue planet through interstellar space depends on the gravitational landscape around it. Its path forms a long curve shaped by the combined pull of many stars. When it passes near a star, even at great distances, its trajectory changes slightly. Most of these changes are small, producing gentle adjustments rather than dramatic alterations. A rare close encounter may cause a more pronounced shift. In rare cases, a planet can even be captured by a new star, becoming part of a different planetary system. More often, the planet continues its solitary travel without joining another orbit. The surfaces of rogue planets tell stories of their earlier environments. Craters, fractures, or frozen plains may preserve traces of past heating, volcanic activity, or atmospheric processes. Chemistry locked within deep layers reflects the conditions of the disk where the planet initially formed. Even as the outer layers freeze, internal structure remains connected to its distant past. This makes rogue planets valuable markers of planetary diversity. Their compositions reflect processes that occurred across the galaxy, long before their journeys carried them far from their birthplaces. Although difficult to detect, rogue planets may be common. Observations suggest that many systems undergo periods of instability that can eject planets into interstellar space. Since these planets emit little light, they are seen only when they pass in front of background stars or reveal themselves through faint heat signatures. Each detection adds to the understanding of how planetary systems evolve and how often their arrangements change over time. The presence of these wanderers shows that the architecture of planets is not always stable. Many worlds experience migration, growth, or ejection as their systems mature. As a rogue planet moves through regions of varying density, its surroundings influence it in subtle ways. Passing through a dense cloud may deposit small amounts of dust on its surface. Moving into thinner regions exposes it to higher levels of cosmic radiation. These exposures shape the chemistry of the frozen layers. Over millions of years, each environment leaves a small imprint. The planet becomes a drifting archive, carrying layers of information about the portions of the galaxy it has crossed. These solitary travelers remind us that stars are not the only centers of motion in the Milky Way. Worlds can exist independently, moving according to the long, patient pull of the galaxy as a whole. Their slow, enduring journeys highlight the variety of paths that matter can take as it moves through interstellar space. Gravity shapes the movements of travelers throughout the galaxy in ways both subtle and profound. Even across distances measured in trillions of kilometers, its influence persists. When two stars pass near each other, their gravitational fields interact, altering the paths of any surrounding material. These interactions may be gentle, producing only small adjustments in direction, or they may create significant shifts that change the fate of entire planetary systems. Gas, dust, comets, and planets all respond to these influences, following curved trajectories determined by the distribution of mass around them. In young star-forming regions, gravitational encounters occur more frequently. Stars often form in clusters where distances between them are small compared to the wider galaxy. As these newborn stars move within the cluster, they pass close enough to affect each other's planetary disks. A slight gravitational pull over thousands of years may tilt a disk, stretch it, or shift material outward. In more dramatic cases, a passing star can send comets or small planets into new orbits, setting them on long journeys that eventually carry them away from the region where they formed. Even in regions where stars are far apart, gravity plays an essential role in shaping the large-scale flow of matter. Molecular clouds respond to the gravity of nearby stars, slowly drifting toward areas of higher mass. Dust grains feel this pull too, though their low mass allows other forces such as radiation and turbulence to compete. When a cloud passes near a massive object, its outer layers may be drawn inward, creating curved paths that guide material along new directions. These changes often occur over millions of years, yet they influence the overall distribution of matter across spiral arms and galactic structures. Gravity also affects how travelers interact with smaller structures. A comet passing near a star may be accelerated or slowed depending on its approach. Some comets gain enough speed to leave the star's influence entirely. Others become trapped into long elliptical orbits that take them deep into the outer regions before returning again. These long-period orbits show how gravity can shape paths that span enormous distances. Dust grains passing near dense pockets within clouds may be pulled into the region, contributing to the buildup of material that will one day form stars. Gravitational interactions can also cause fragmentation within clouds. When regions become too dense, collapse begins, drawing material inward. As matter moves toward the center, outer layers may stretch or shear, creating new flows and boundaries. Dust grains and molecules caught in these motions follow paths that depend on their distance from the collapsing region. Some fall inward and become part of the early stages of star formation. Others are displaced outward and driven into nearby areas where they mix with different material. Over longer timescales, gravity produces large-scale organization across the galaxy. Stars orbit the galactic center in broad, sweeping curves. Their combined gravitational influence helps maintain the structure of spiral arms, pulling gas and dust into patterns that persist across millions of years. This motion generates regions where matter accumulates, creating new environments for future travelers. The distribution of star clusters, clouds, and filaments all reflect the underlying shapes created by gravitational dynamics. Even small gravitational influences accumulate over time. A dust grain passing near a cloud may change direction slightly, A planet in a distant system may shift its orbit due to the slow movement of a neighboring star. These changes may be nearly invisible in the moment, yet they build toward new paths that guide matter into different regions. Gravity acts as the quiet sculptor of motion, shaping each traveler's journey from one environment to another across the vast landscape of the Milky Way. Solid fragments that drift through interstellar space offer another perspective on how matter moves between stars. These fragments include rocky bodies that once formed within planetary systems before being cast out through gravitational interactions. Unlike comets, they contain little to no volatile ices. Their surfaces remain dark and inert as they travel, shaped only by slow exposure to radiation and impacts from tiny particles. Over long durations, these influences sculpt irregular forms that differ from the rounded shapes, often found in more densely populated regions. The origins of interstellar rocky fragments vary. Some may come from collisions between early forming planets or large asteroids. Such collisions can break apart solid bodies, sending pieces outward at speeds high enough to escape their systems. Others may be remnants of planetesimals that never grew into full planets, but were thrown into chaotic orbits during periods of instability. No matter their origin, once these fragments enter interstellar space, they begin a new phase of travel, influenced by forces that act over immense timescales. Their surfaces change slowly as they move through different environments. In regions with strong radiation, the outer layers darken as molecules break apart and reform. Micrometeoroid impacts create small pits and fractures, gradually reshaping the texture of the surface. These changes accumulate over millions of years, producing forms that reveal details about the environments they encountered. A fragment that spent time in a dense cloud may carry dust deposits. One that drifted through more diffuse gas may show patterns caused by tiny impacts and chemical alteration. When these rocky travelers pass near stars, they reflect only a small amount of light. This makes them difficult to detect unless they approach closely or cross paths with a bright background source. Their motion through the solar system, when observed, often reveals unusual trajectories that do not match objects bound to the sun. Such paths indicate that these visitors come from beyond, carrying the history of environments that may differ greatly from our own. Chemical analysis of such bodies, when possible, provides valuable information about those distant environments. Their mineral compositions can show whether they formed in warm or cold regions, whether the disk they emerged from contained abundant heavy elements, or whether it experienced high levels of radiation. The structure of the rock, the presence of certain isotopes, or the patterns within crystalline formations all serve as clues. These clues help scientists understand the diversity of planetary formation across the galaxy. Interstellar rocky fragments do not usually influence their surroundings strongly, yet their presence contributes to the overall mixing of matter. As they drift, they pass through regions where dust and gas collect. Some may be captured temporarily by gravitational forces within clouds or near-forming stars. Even a brief capture can alter the distribution of material, adding small amounts of rock and metal that later become part of new structures. In rare cases, a fragment may become permanently bound to a new star, becoming part of its population of asteroids or minor planets. Their journeys highlight the quiet persistence of solid matter. Despite their simplicity, these rocky travelers carry traces of the processes that shaped them long ago. Their slow movement through the galaxy contributes to the ongoing exchange of material that underlies cosmic evolution. They are reminders that even the smallest fragments participate in the long cycle of motion that moves matter from one generation. In the cold interiors of molecular clouds, chemistry unfolds in ways that differ from any environment found near stars. Temperatures fall low enough that atoms move slowly, allowing them to settle onto the surfaces of dust grains. These grains become tiny platforms where molecules form through quiet, gradual interactions. Hydrogen atoms bind first, creating simple compounds. Oxygen, carbon, and nitrogen join next, forming water, carbon monoxide, ammonia, and methane. With time, these compounds build outward into icy layers that coat the grain. These icy mantles grow in complexity as the grain moves through different regions. A shift into a slightly warmer zone may cause some molecules to migrate across the surface before refreezing in new arrangements. Exposure to ultraviolet light can break bonds within the upper layers, freeing atoms that later recombine into different molecules. Cosmic rays contribute energy that allows new reactions to occur even in the coldest areas. Each of these processes adds to the chemical diversity of the grain's surface. Turbulence within the cloud stirs grains into new environments. A grain may drift from a shadowed interior into a region where nearby stars produce faint illumination. Temperatures rise enough to alter some of the ice, while other layers remain stable. Molecules that evaporate in warmer zones enter the surrounding gas, contributing to the distribution of chemistry throughout the cloud. When the grain returns to colder regions, new layers of ice may form. The grain's structure becomes a record of how temperature and radiation varied across its journey. The density within molecular clouds supports more complex chemistry than diffuse regions can sustain. Molecules collide more frequently, creating opportunities for additional reactions. Some of the compounds produced in these environments serve as the building blocks for more intricate organic structures. Dust grains help by providing surfaces where reactions can occur more easily. Without these grains, many molecular combinations would proceed too slowly to matter. Their presence accelerates the growth of chemical diversity within the cloud. As grains coated with layered ice drift toward denser zones, their chemical content becomes increasingly important. When these regions begin to collapse under gravity, the grains fall inward with the gas. Heating during early stages of collapse causes some ice layers to release molecules into the gas phase. These molecules influence how the gas cools and how it responds to changing pressures. Others remain locked within the grain and become part of the solid material that will later form planets and smaller bodies. The chemistry that develops in molecular clouds does not stay in one place. Turbulence and large-scale flows carry molecules outward, allowing them to spread into the surrounding medium. Each molecule that escapes into warmer or more diffuse regions becomes a traveler shaped by its earlier environment. Some may drift for long periods before entering another cloud where new reactions occur. Others remain in the diffuse medium, contributing to its chemical makeup. These processes illustrate how molecular clouds act not only as birthplaces for stars but also as factories where the galaxy's chemical richness grows. The travelers that emerge from these environments carry layered histories reflecting temperature shifts, radiation exposure, and changing densities. As they move outward, they seed the wider medium with material that will later join new generations of clouds. In this way, molecular cloud chemistry becomes a driving force behind the diversity of matter found throughout the Milky Way. Organic molecules found in interstellar space are among the most intricate travelers in the galaxy. They form in environments where dust, grains, radiation, and cold temperatures interact in balanced ways. Simple molecules such as methane, ammonia, and carbon monoxide can combine on the surfaces of dust grains, creating more complex structures over long periods. Ultraviolet light from distant stars provides enough energy to break bonds in these molecules. The freed atoms then recombine into new arrangements, slowly building complexity within the icy mantles that coat the grains. Once formed, these organic compounds travel with the grains through regions of varying temperature and radiation. A shift into warmer zones may release some molecules into the gas phase. Others remain frozen onto the grain until they reach environments where new reactions can occur. This interplay between evaporation, condensation, and chemical change creates layers of organic material that reflect different stages of the grain's journey. The composition of these layers provides clues about the conditions the grain experienced in earlier parts of its path. Organic molecules also drift freely in the gas. In diffuse regions, ultraviolet radiation encourages reactions that lead to the creation of certain organic species. Although these molecules may not remain stable for long, turbulence spreads them into nearby areas where they combine with dust grains or mix with denser gas. In colder regions, the molecules attach to grains and become part of the icy layers that form there. Over time, this cycle of creation, destruction, and recombination shapes the organic chemistry of entire clouds. As dense regions of molecular clouds begin to form, organic molecules play an increasingly important role. Their presence helps determine how the gas cools and how energy flows through the cloud. Molecules that absorb infrared radiation can release it again, allowing the cloud to shed heat more efficiently. This cooling influences how quickly the region collapses under gravity. The organic compounds carried by dust grains also contribute to the chemical makeup of the forming structures. When temperatures rise, the grains release some of their stored molecules, enriching the surrounding gas. These drifting organics play important roles in the chemistry of new worlds. When grains carrying organic mantles become part of a collapsing cloud, their molecules are preserved within the material that forms planets, asteroids, and comets. Some of these molecules eventually find their way to the surfaces of young planets, where they may participate in further chemical evolution. Although this story does not speculate beyond established science, it is clear that organic travelers contribute essential ingredients to planetary environment. The distribution of organic molecules across the galaxy is shaped by large-scale flows. As material moves from diffuse regions into dense clouds and back again, organics are carried along these paths. Turbulence stirs them into new environments, allowing chemistry to spread widely. When stars form and release energy into nearby regions, some organic compounds break apart, while others survive to join future clouds. These cycles continue across vast timescales, ensuring that organic molecules travel far from the places where they first emerged. The presence of such molecules across many regions of the Milky Way shows how interconnected the galaxy's chemical evolution has become. Organic travelers carry histories shaped by many environments. Their movement links the diffuse medium, molecular clouds, star-forming regions, and planetary systems into a single dynamic network. Each stage of this journey contributes to the richness of the interstellar medium, preparing it for the next cycle of star and planet formation. Light itself is among the most far-reaching travelers in the galaxy. Photons released from stars, nebulae, and energetic events move through space at extraordinary speed, crossing vast distances without physical contact. Each photon carries information about the environment in which it formed, such as the temperature of a star's surface or the motion of gas within a cloud. Because the interstellar medium is so thin, most photons travel unhindered, passing through regions of varying density and composition without being absorbed or scattered. Starlight shapes the behavior of matter as it moves. When photons strike dust grains, they provide both energy and momentum. The energy warms the grain slightly, influencing how molecules attach or detach from its surface. The momentum exerts a gentle push that nudges the grain away from the star. These effects accumulate slowly, creating outward flows that carry dust and gas into new regions. In areas near bright stars, the combined influence of many photons can carve cavities into nearby clouds, altering the distribution of material on large scales. Not all photons travel with equal ease. Ultraviolet light interacts strongly with certain molecules, breaking chemical bonds and initiating new reactions. Infrared light, on the other hand, is more likely to pass through dust clouds, carrying information about colder regions. Visible light lies between these extremes, revealing structures illuminated by stars. The variety of photon interactions shows how light contributes to the chemical and physical evolution of the interstellar medium. Photons from distant galaxies and ancient stars also pass through the Milky Way. Their paths reveal the presence of dust through the way they are reddened or dimmed. When light encounters a dust grain, the grain may absorb some wavelengths and scatter others, altering the appearance of the underlying source. These small changes accumulate along the photon's path, providing observers with clues about the amount and type of dust between the source and the observer. In this way, light serves as a probe that maps the structure and content of the interstellar medium. The movement of light is influenced by gravity as well. When a photon passes near a massive object such as a star or black hole, its path curves slightly. This bending of light creates subtle distortions in the images of distant objects, helping astronomers study the mass distribution within galaxies. The phenomenon does not slow the photon, but it alters the direction in which it travels. Over large distances, such curvature becomes part of the complex pattern of paths that photons trace across the universe. Light also plays a role in triggering star formation. When radiation from young, hot stars strikes nearby clouds, it compresses the gas and dust at the edges, sometimes pushing the material into denser configurations. These compressed regions may then collapse under their own gravity, forming new stars. The process shows how energy from one generation of stars contributes to the birth of the next, linking different stages of the galaxy's evolution through the movement of light. For a listener settling quietly, there is a gentle parallel between the steady flow of photons and the gradual drift toward rest. Light travels without hurry, covering vast distances with calm and steady motion. In the same way, you can allow your mind to soften and drift at its own natural pace, without pressure or expectation, as the story continues its path through the wide spaces between stars. Photons that leave their sources continue onward long after the events that created them have ended. Many will travel across the galaxy without being absorbed, carrying their messages into future environments. Through their journeys, they illuminate not only the objects they encounter but also the vast, quiet spaces that lie between. Neutrinos are among the most elusive travelers in the galaxy. These tiny particles pass through matter almost without interaction, allowing them to move through stars, planets, and clouds, as if they were nearly transparent. Every second, countless neutrinos created in the cores of stars and during energetic cosmic events stream outward in all directions. Their lack of electric charge and extremely small mass enable them to maintain high speeds and follow long, uninterrupted paths. Neutrinos originate in environments where nuclear reactions occur. In the cores of stars, hydrogen atoms fuse into helium, releasing energy and producing a continuous flow of neutrinos. These particles escape the star within moments, unlike photons that may take long periods to reach the surface. During supernova explosions, even larger numbers of neutrinos are released in a sudden burst, carrying information about the extreme conditions deep within the collapsing star. Because neutrinos interact so weakly with matter, they leave these environments largely unchanged and provide rare insights into the processes occurring in otherwise hidden regions. As neutrinos travel through interstellar space, they pass through clouds, dust, and stars without slowing. Only on rare occasions do they collide with atoms. When such a collision occurs, it produces signals that can be detected by sensitive instruments on or beneath Earth's surface. These detections allow researchers to trace some of the paths neutrinos have taken, revealing clues about their origins. Although individual neutrinos cannot be followed back to precise locations, the patterns of their arrival help build a picture of the nuclear activity within the galaxy. The weak interaction of neutrinos with matter also means they do not contribute significantly to the physical shaping of interstellar environments. They neither push dust grains nor alter gas in ways that influence large-scale flows. Instead, their significance lies in the information they carry. Through their detection, scientists can learn about the interior conditions of stars, the processes that drive supernovae, and the distribution of nuclear activity across the galaxy. The behavior of neutrinos is influenced slightly by the gravitational fields they encounter. When passing near a massive object, their paths curve in a way similar to photons. Yet because neutrinos interact so rarely with matter, their motion remains almost entirely smooth. This smoothness allows them to travel across immense distances without deviation. As a result, they serve as messengers that cross the galaxy with clarity, connecting regions far from one another. Neutrinos also reveal how interconnected stellar processes are. A burst of neutrinos from a supernova may reach distant parts of the galaxy long before the expanding gas and dust become visible. These early signals help identify where new elements and shock waves will arise. They also confirm that the life cycle of stars affects the galaxy on both large and small scales. Through neutrinos, the quiet workings of stellar cores become part of a wider narrative of motion and transformation. Some neutrinos detected on Earth likely originated outside the Milky Way, produced by energetic events in distant galaxies. These particles demonstrate that interstellar and intergalactic processes share common mechanisms. Their arrival provides glimpses into environments far beyond the reach of photons or matter. Each neutrino that reaches Earth carries a faint record of processes that unfolded across unimaginable distances. The journeys of neutrinos show that interstellar travel is not limited to physical matter. Even particles that rarely interact with their surroundings play a role in the galaxy's continuous flow of energy and information. Their motion contributes to the broader picture of how stars evolve, how galaxies develop, and how the universe maintains its interconnected structure. Large-scale motion within the Milky Way shapes the journeys of countless travelers. The galaxy rotates slowly, completing one full turn over hundreds of millions of years. Despite this long period, the rotation influences how stars, gas, and dust move on enormous scales. Each part of the galaxy follows a curved path around the center, guided by gravity from the combined mass of stars, dark matter, and gas. This rotation establishes broad patterns that carry travelers along predictable arcs. Spiral arms form within these rotating structures as regions of higher density. They are not rigid formations but patterns where material is more concentrated. As stars and clouds move around the galaxy, they pass through these arms, experiencing environments richer in gas and dust. The increased density within an arm encourages the formation of new stars and influences how clouds evolve. Travelers entering these regions encounter stronger gravitational pull and more frequent interactions. Dust grains may collect more ice in cooler pockets, while molecules may form or break apart as radiation levels shift. The movement of gas through spiral arms is influenced by pressure differences. As clouds enter an arm, they compress slightly, increasing their density. This compression may trigger the earliest stages of collapse within some regions. After clouds move beyond the arm, they expand again, altering the balance between gas and dust. These repeating cycles contribute to the long-term structure of the galaxy, guiding where new generations of stars appear. The travelers within these clouds experience these shifts gradually, following the wider motion of the galaxy. Galactic rotation also affects how streams of gas move between different regions. In some areas, gas flows inward toward the galactic center. In others, it drifts outward, spreading material across broader distances. Dust grains and molecules follow these flows, carried along by the shifting pressure patterns. Over millions of years, these movements redistribute material from one part of the galaxy to another. Travelers formed near the inner regions may eventually drift outward into calmer environments, while those originating in the outer galaxy may be drawn toward denser zones. Magnetic fields stretch across the disk of the galaxy, influencing how charged particles move within this rotating environment. These fields shape the flow of ionized gas and contribute to the organization of spiral structures. Charged particles spiral along magnetic lines, following paths that shift gradually as the galaxy rotates. Dust grains with small electric charges respond as well, drifting in directions influenced by both rotation and magnetic shaping. These interactions create complex patterns that determine how material spreads across the disk. Stars themselves move according to the galaxy's gravitational framework. Some follow nearly circular paths, while others travel on elongated or inclined orbits. As they move, their gravitational pull affects nearby material. A star passing through a cloud may compress the gas or draw dust grains inward. Over long periods, these small influences contribute to the redistribution of matter. The combined motions of many stars create a dynamic environment where travelers experience continually changing gravitational landscapes. Large-scale motion also includes the slow rise and fall of clouds as they move above and below the galactic plane. These vertical oscillations create additional variation in the environments through which travelers pass. A cloud drifting upward may encounter weaker radiation fields, while one moving downward may pass through denser regions. Dust grains, molecules, and larger bodies respond to these changes, altering their chemistry and motion accordingly. Across these vast scales, the galaxy maintains a rhythm shaped by rotation, gravity, and magnetic structure. Travelers follow this rhythm as they drift through arms, clouds, and interarm regions. Their paths reflect the long, continuous movement of the Milky Way, linking local environments to the broader framework that guides the distribution of matter. In certain regions of the galaxy, gas and dust do not remain evenly mixed. Instead, they gather into cloud complexes that move together through space. These complexes form when large-scale flows converge, bringing material into shared motion. Within such a structure, clouds maintain relative proximity while drifting across hundreds of light years. Their paths reflect the gravitational influence of nearby stars, the shape of spiral arms, and the flow of gas through the galactic disk. Travelers within these complexes experience environments that change gradually as the structure evolves. Cloud complexes contain a mixture of diffuse gas, dense molecular regions, and transitional layers between them. As the complex moves, each region responds differently to external forces. Diffuse gas is easily shaped by pressure changes and turbulence. Dense regions resist disruption more strongly, maintaining their structure even when surrounded by active motion. Dust grains drift between these regions, crossing boundaries where temperature and radiation levels shift. Their motion records the changing conditions within the complex. The interactions between clouds within a complex create additional patterns. When two clouds pass near each other, their outer layers mix, exchanging dust and molecules. Such encounters may also compress gas at the boundary, encouraging the formation of new dense regions. Over long durations, these repeated interactions contribute to the complex's internal structure. Travelers moving through these regions experience varying densities, chemical compositions, and levels of turbulence. Cloud complexes also respond to energy released by nearby stars. Hot stars at the edges of a complex may heat surrounding gas, producing expanding shells that push into the interior. These shells alter the flow of material and influence how dust grains drift. If the complex contains regions shielded from these sources, cooler pockets persist, allowing ices and molecules to remain stable. The balance between heating and cooling determines the chemical diversity within the complex. As the entire structure moves through the galaxy, it interacts with the larger environment. Passing through a spiral arm compresses portions of the complex, while leaving others unchanged. Moving into an interarm region may allow the complex to expand. Magnetic fields contribute by directing flows along certain paths, shaping the distribution of gas and dust. These influences act slowly, yet they guide the long-term evolution of the cloud complex. Travelers within these moving structures follow paths shaped by both internal and external forces. A dust grain may drift from a warm, diffuse envelope into a dense, cold core, where it becomes coated with ice. Later, turbulence may carry it outward again, altering its chemistry. A molecule formed in one region may be destroyed in another, only to reform elsewhere. These cycles of change create a rich chemical landscape that moves with the complex. Over millions of years, cloud complexes disperse, leaving their material to join new environments. Some parts collapse into stars, forming clusters that continue moving along the galaxy's rotation. Other parts drift outward, contributing diffuse gas to surrounding regions. Dust grains released from dense regions spread into the wider medium, carrying their layered histories with them. The dispersal of the complex ensures that its chemical contributions extend far beyond its original boundaries. These large moving structures demonstrate how matter in the galaxy follows not only individual paths but collective ones. Travelers within a cloud complex share motion shaped by a combination of gravity, rotation, turbulence, and magnetic structure. Their journeys contribute to the constant reshaping of the interstellar medium, adding complexity to the patterns that guide the evolution of the Milky Way. As cloud complexes move through the galaxy, some regions evolve into highly structured networks, shaped by pressure differences, turbulence, and magnetic patterns. These networks link clouds together through channels of gas that guide the motion of dust, grains, and molecules. Material flowing through these channels may travel great distances before settling into calmer regions. The interconnected nature of these pathways allows travelers from one part of the galaxy to influence the chemistry and structure of distant locations. These channels often form where large-scale flows compress gas into elongated shapes. Unlike the dense filaments found deep within molecular clouds, these structures are more diffuse, spanning wide areas between major clouds. They serve as bridges that carry material from one environment to another. Dust grains moving through such channels experience gradual changes in temperature and density, altering their surface chemistry. Molecules drift along with the gas, entering regions where new reactions become possible. Magnetic fields provide additional structure to these flows. In some areas, the fields run parallel to the channels, aligning the motion of charged particles and guiding dust grains that carry slight electric charges. In other areas, twisting or diverging field lines create branching patterns that lead to multiple directions of flow. This magnetic shaping helps determine how material spreads from one region to another. A dust grain following one branch may enter a warm, diffuse zone, while another drifting along a different branch may be carried toward a cooler, denser cloud. Interactions occur where channels intersect. These junctions become sites where gas from different regions meets, mixing molecules that formed under distinct conditions. Collisions between gas streams generate turbulence, allowing dust grains to cross from one flow to another. Such intersections enrich the chemical diversity of their surroundings. Molecules created in cold, shielded environments blend with those shaped by warmer, more illuminated regions. Through these exchanges, channels become agents of chemical distribution across the galaxy. Channels also influence the development of new structures. Gas flowing into a molecular cloud through a narrow corridor may carry enough momentum to compress the cloud's outer layers, affecting its internal dynamics. Dust grains entering such zones may contribute to ice accumulation in the cold interior or help regulate heating near the surface. Each of these interactions reflects the long-term influence of material that originated far outside the cloud's boundaries. The movement of travelers through these networks is gradual but persistent. A molecule may drift along a channel for thousands of years before encountering a region where it attaches to a dust grain. A grain may pass through warm pockets that modify its icy mantle before moving into cooler zones where new layers form. These slow adjustments shape the composition of matter that will later join new clouds or star-forming regions. The channels act as conveyors that distribute both mass and chemistry across large distances. Over time, some channels dissipate as pressure gradients shift or turbulence reorganizes. New ones form in their place, reflecting the dynamic nature of the interstellar medium. Travelers caught within these flows continue onward, guided by forces that change slowly but steadily. Their paths reveal the interconnected structure of the galaxy, where no region remains isolated. Material moves between clouds, across spiral arms, and through diffuse envelopes, linking environments separated by vast distances. These networks of channels highlight how large-scale flows contribute to the mixing of matter throughout the Milky Way. Travelers carried along these paths become part of a broader cycle that redistributes material across the galaxy. Their motion ensures that the chemical and physical diversity created in one region can influence the development of others, making the interstellar medium a deeply interconnected system. As material flows through channels and cloud complexes, some regions evolve into environments where gravity begins to assert greater influence. These regions often emerge where gas accumulates gradually, either through large-scale compression or through the steady inflow of matter from surrounding areas. Over long periods, the density within such zones increases until gravitational attraction becomes strong enough to draw additional material inward. This marks the early transition from diffuse interstellar gas to the structures that eventually give rise to stars and planetary systems. Within these growing regions, the behavior of travelers changes. Dust grains that once drifted freely now begin to follow inward paths, shaped by the deepening gravitational well. Their motion becomes more organized, moving along gentle curves toward the developing core. Gas molecules accompany them, colliding more frequently as densities rise. These collisions help distribute heat and influence how quickly the gas can cool. Cooling plays a critical role in determining whether gravitational collapse can continue. If the gas sheds heat efficiently, the region compresses further. If not, pressure may temporarily halt contraction. Turbulence within these zones does not disappear but instead becomes intertwined with the gravitational motion. Areas of higher density may form briefly before dispersing, while others persist and strengthen. Dust grains caught in these motions experience a shifting environment where temperature varies from warm outer layers to cooler interiors. In the colder regions, molecules bind readily to grain surfaces, adding new layers to their icy mantles. As grains move inward, these layers may evaporate again, returning molecules to the gas phase and influencing the chemistry of the forming core. Magnetic fields also play an important role. In some regions, magnetic strength is sufficient to resist collapse, slowing the inward flow of material. Charged particles tied to magnetic field lines influence how gas moves, creating distinct pathways through which matter can enter the developing core. In areas where the magnetic field weakens or becomes distorted, gas flows more freely, accelerating collapse. Dust grains that carry small electric charges respond indirectly to these patterns, drifting preferentially along routes shaped by both gravity and magnetic tension. Over time, these processes guide material into structures increasingly defined by rotation. Even slight initial spins become more pronounced as matter contracts. Conservation of angular momentum causes the region to flatten into a disc-like shape. Dust grains begin to move in circular orbits rather than drifting at random. Gas flows become more coherent, forming spiraling patterns that steadily deliver material inward. Within this environment, chemical composition varies with distance from the center. Warmer regions near the core lose ices, while cooler outer areas preserve them. These early disks represent the initial stages of what will one day become planetary systems. Travelers entering the disk contribute their accumulated histories to its evolving chemistry. Dust grains bring layered records of earlier environments. Molecules released from evaporating ices enrich the gas. Material arriving from channels and cloud complexes introduces diversity from distant regions. The disk becomes a collection point where contributions from many parts of the galaxy gather into a single structure. Although collapse and disk formation mark significant transitions, the process remains gradual. Travelers continue moving through the system, influenced by forces that act over long periods. Some grains fall inward and are destroyed by heat. Others survive and join concentrations where larger solid bodies may eventually grow. Molecules mix, reform, and redistribute, shaping the conditions under which future planets will emerge. This stage illustrates how interstellar travelers contribute to forming the foundations of new worlds. Their paths through cold clouds, turbulent channels, and gravitational wells build layers of chemistry and structure that converge into the early architecture of planetary systems. Each traveler carries a piece of the galaxy's history into these evolving environments. As the forming disk grows, movement within it becomes increasingly organized. Gas and dust do not drift randomly but follow circular paths shaped by gravity, pressure, and rotation. Inward flow continues as material spirals toward the central mass, but the distribution of that flow changes with distance. Inner regions experience stronger gravitational pull and higher temperatures. Outer regions remain cooler and more diffuse. These gradients produce zones where specific forms of matter accumulate, each influencing the structure of the disk. Dust grains entering the disk begin to settle toward its midplane. Collisions with gas molecules slow their vertical motion, guiding them gradually downward. Over long periods, this settling concentrates grains into a thin layer, where collisions between solids become more frequent. Many of these impacts are gentle enough to allow grains to adhere, forming clusters that move differently from individual particles. These early aggregates influence their surroundings by stirring the gas slightly and altering local density patterns. In time, regions within the midplane may develop concentrations of solid material that represent the earliest steps toward forming larger bodies. Gas responds to the disk structure as well. In warmer regions near the center, molecules move quickly and remain in the gas phase. In cooler regions farther out, ices can form and remain stable. This separation of volatile and non-volatile substances creates boundaries that determine which materials remain close to the forming star and which remain in the outer disk. A dust grain traveling inward may lose its icy coatings as it crosses these boundaries. Another moving outward may accumulate fresh layers as it enters colder zones. These transitions shape the chemical diversity that future planetary bodies inherit. Turbulence adds complexity to these motions. It disrupts simple circular paths, creating small eddies that mix material across local scales. Dust grains may be lifted slightly above the midplane before settling again. Gas may shift between warmer and cooler pockets, redistributing molecules as it flows. Turbulence also contributes to maintaining the disk's thickness by counteracting the gravitational pull that draws material toward the midplane. Without this constant stirring, the disk would become even thinner and more prone to forming tightly confined layers of solids. Pressure differences within the disk produce additional movements. Gas in outer regions orbits more slowly than solids, causing dust grains to feel a slight headwind as they travel. This interaction removes a small amount of momentum from the grains, causing them to drift inward over long periods. The rate of this drift depends on grain size. Smaller particles remain closely tied to gas flow and move inward slowly. Larger particles drift more rapidly, allowing them to cross significant distances in shorter times. This movement helps transport materials formed in cold regions into warmer areas where chemistry evolves further. Some regions within the disk develop increased concentrations of solids due to subtle interactions between gas flow and particle motion. These concentrations may grow as additional material drifts into them. Over time, the combined effects of settling, drifting, and local accumulation create patches where solids become dense enough to influence each other's movement more strongly than the surrounding gas. These patches represent an important step toward forming the larger structures that will eventually become planetesimals. As the disk continues to evolve, each traveler contributes to its growing complexity. Dust grains bring layered histories shaped by earlier environments. Molecules released from ices enrich the gas with chemistry that reflects distant parts of the galaxy. Larger clusters of solids represent the earliest building blocks of planetary systems. Through their combined motion, the material within the disk creates patterns that shape the system's long-term development. The formation of the disk marks a key stage in the journey of interstellar travelers. Their slow inward drift and gradual assembly demonstrate how matter from many regions converges into a single structure where new worlds begin their development. As solid material within the young disk accumulates into increasingly larger clusters, interactions between these growing bodies become more significant. Small aggregates collide and merge, forming pebbles and eventually larger fragments. These bodies respond differently to gas flow than dust grains do. Their increased mass reduces the influence of turbulence and radiation pressure, allowing gravity and momentum to play a larger role in shaping their motion. This marks a new phase in the journey of interstellar travelers, where individual histories blend into the early architecture of forming planetary systems. In regions where concentrations of solids grow dense enough, their combined gravity begins to draw in nearby particles. This process enhances the local accumulation of material. Over time, some of these clusters reach sizes large enough for gravity to dominate their structure. They become planetesimals, bodies that can attract additional mass and influence their surroundings. These early objects may drift inward or outward depending on interactions with the disk's gas. Their motion reshapes the flow of material around them, creating lanes or gaps that guide the paths of smaller particles. Temperature differences within the disk continue to influence how material moves and evolves. In warmer inner regions, ices have evaporated, leaving behind rocky and metallic particles. These materials collide to form solid cores. In colder outer regions, ices remain stable, allowing larger bodies to form with significant amounts of frozen material. These differences contribute to the diversity of planetary compositions that later emerge. A body forming near the center may become dense and rocky, while one forming farther out may contain thick layers of ice. Gas within the disk interacts with growing bodies in various ways. As a planetesimal moves through gas, it experiences a drag force that influences its orbit. Small planetesimals may drift inward gradually, while larger bodies resist this motion more effectively. Gas flow can also concentrate solids by pushing them toward pressure maxima within the disk. These regions become favorable sites for continued growth, attracting more material and forming larger structures. Collisions between growing bodies are common during this stage. Some impacts are gentle and lead to merger. Others are energetic, breaking apart objects into smaller fragments. These fragments rejoin the disk's population of solids, continuing the cycle of growth and erosion. Over long durations, The system gradually sorts itself into regions dominated by particular sizes of bodies. Larger planetesimals tend to clear their orbits of smaller fragments, while smaller particles remain tied more closely to the movement of gas. The chemistry of the disk evolves alongside these physical changes. As solid bodies grow, they lock certain elements into their interiors. Meanwhile, gas phase molecules continue to shift based on temperature and radiation. Dust grains that avoid incorporation into larger bodies drift through these changing environments, collecting or releasing molecules as conditions vary. Each of these motions contributes to the emerging structure of the disk, determining how material will eventually be distributed among future planets, moons, and smaller bodies. Throughout this stage, movement remains a defining feature. The earliest travelers, once drifting through diffuse interstellar clouds, now participate in the formation of stable orbits and complex interactions. Their paths carry them into regions where they collide, merge, or fragment. The shapes of their journeys reflect the forces at work within the disk, guiding the transformation of scattered particles into the building blocks of larger worlds. The emergence of planetesimals marks a crucial point in the long process of planetary formation. It represents the moment when interstellar travelers become part of cohesive structures that will continue to grow and evolve. Their contributions shape the early layout of the planetary system, creating a foundation upon which later development unfolds. The solid bodies forming within the young disk continue to grow as they sweep through their orbits, gathering smaller fragments and dust grains. Their motion creates subtle disturbances in the gas around them, shaping currents that influence how material flows through the disk. In regions where these bodies become large enough, they begin to carve pathways through the gas, leaving behind faint patterns that reveal their presence. These pathways become traces of the early architectural framework of the system, guiding other travelers into repeating patterns of motion. As these developing bodies grow more massive, their gravitational influence strengthens. They collect material from broad zones, drawing in fragments that cross their paths. Some bodies grow quickly, becoming dominant features in their regions. Others remain small and continue drifting through the disk until they collide with larger structures or break apart. The diversity of outcomes reflects the complex environment in which they evolve. Every collision, merger, and scattering event contributes to the texture of the developing planetary system. Temperature gradients continue to play a central role in shaping the composition of these bodies. In the inner regions of the disk, warmth prevents ices from forming stable layers. The bodies that grow there remain largely rocky or metallic, reflecting the materials available at those temperatures. Farther from the center, colder conditions allow ices to accumulate, and bodies in those regions incorporate frozen water and volatile molecules into their structures. This distinction becomes crucial for determining the long-term characteristics of planets and moons that will eventually form. Gas flow within the disk evolves as solid bodies grow larger. When a developing object reaches a certain size, it begins to influence gas pressure in its surroundings. The gas may slow in some regions and accelerate in others, redirecting the paths of nearby dust grains. These shifting patterns create zones where smaller solids accumulate. As these concentrations build, some areas produce new planetesimals, while others remain relatively empty. The disk becomes a dynamic environment where motion guides the gradual assembly of complex structures. Dust grains that avoid incorporation into larger bodies continue to drift through regions shaped by temperature, pressure, and gas motion. Their icy mantles evolve as they cross boundaries between warm and cold zones. Molecules evaporate and refreeze, reshaping the chemistry carried within these grains. When these grains eventually join a forming body, they contribute their layered histories to its composition. A planet forming in a warm region may still contain traces of distant environments if its material originated in colder parts of the disk. The gradual motion of these travelers mirrors a quieter rhythm, one that unfolds without haste. Just as material drifts inward, outward, and around the disk in patient cycles, your thoughts can ease into a slower pace as well. There is no need for stillness to arrive all at once. A gentle settling, like the steady movement of dust and gas within these forming worlds, can unfold naturally as you continue to listen. Over long durations, the largest of these growing bodies may begin to clear broad lanes within the disk, dividing it into regions that evolve differently from one another. These cleared paths shape how gas and dust move, influencing where additional bodies can form and how they grow. Smaller solids caught in these patterns may find themselves drawn towards specific zones, joining the emerging architecture of the system. Each traveler contributes to this structure, whether by merging with larger bodies or by shaping the motion of the gas around them. The formation of these early structures reveals how interstellar travelers become part of larger, coherent systems. Their long journeys through clouds, channels, and collapsing regions now converge into organized patterns that define the early stages of new worlds. Their motion continues, shaped by forces that guide the development of a system that will one day host planets, moons, and other enduring features. Material within the maturing disk continues to reorganize under the influence of growing bodies and evolving gas flows. As some planetesimals reach larger sizes, their gravitational pull begins to shape the orbits of nearby objects. This influence causes smaller bodies to gather into clusters or disperse into new regions, depending on the direction and strength of their encounters. The disk transforms from a uniform distribution of particles into a patchwork of dynamic zones, each with its own pattern of motion. Gas still plays a central role in directing this movement. In regions where pressure decreases slightly, gas flow changes enough to create pockets where dust and pebbles accumulate. These pockets can become reservoirs that feed growing bodies. Bodies that pass through these zones may collect significant amounts of material, accelerating their development. Over time, some of these bodies become embryos that can influence the disk on larger scales, perturbing orbits and shaping new structures. Temperature gradients maintain their ongoing influence as well. As solid bodies drift through the disk, they encounter regions where volatile compounds evaporate or condense. A body moving inward may lose its icy layers, altering its composition. One moving outward may gather ices that change its surface chemistry. These transitions ensure that material within the disk remains varied, with compositions that reflect both local conditions and the long journeys of the particles that formed them. Collisions continue to shape the disk's evolution. Some encounters occur at low speeds, allowing bodies to merge and grow. Others are more energetic, breaking objects apart and scattering fragments into new paths. These fragments rejoin the population of solids, providing additional material for other bodies to collect. This continuous cycle of accumulation and fragmentation maintains a mixture of particle sizes within the disk, influencing how gas flows and solids interact. The presence of multiple growing bodies creates gravitational patterns that extend across substantial regions. These patterns may form resonances, where bodies settle into orbits whose periods align in regular intervals. Such resonances can either stabilize or destabilize motion. They may guide material into narrow rings or scatter it into distant zones. Over long durations, these resonant interactions contribute to the sculpting of the disk's structure, influencing where planets are likely to form. Gas gradually thins as the disk evolves. Stellar radiation begins to clear material from the outer layers, driving winds that remove small particles or lift gas away from the disk's surface. This process reduces the influence of gas on larger bodies, allowing them to move more freely. As gas density decreases, solid bodies become the dominant contributors to shaping the disk's motion. Their gravitational interactions, collisions, and migrations guide the final stages of the disk's transformation into a planetary system. Dust grains that remain unincorporated continue their long journeys through the evolving environment. Some drift inward and evaporate as they approach warmer regions. Others move outward and join distant parts of the disk. Each grain's path reflects a combination of its origin, its encounters, and the forces shaping the disk at each stage. These grains carry material from multiple regions, ensuring that chemistry once confined to narrow zones becomes distributed more widely. Through these shifting motions, the disk becomes increasingly structured. Zones of growth, fragmentation, and migration appear and change as bodies evolve. The patterns formed by these processes determine where planets will eventually emerge and what compositions they will inherit. Travelers across these regions contribute their histories to the forming system, linking distant parts of the galaxy to the early architecture of new worlds. As the young system evolves, large-scale motions within the disk begin to reflect the combined influence of its growing bodies, the remaining gas, and the remnants of earlier flows. These interactions create patterns that shape not only the formation of planets but the long-term distribution of dust, molecules, and small solids. The result is a dynamic environment where travelers continue to move along paths, guided by gravitational forces, chemical transitions, and subtle variations in pressure. Gas flow decreases gradually as the forming star emits increasing amounts of radiation. This radiation heats the upper layers of the disk, causing some of the gas to expand and drift away into surrounding space. The thinning gas reduces the drag forces acting on larger bodies, allowing them to maintain more stable orbits. Smaller particles remain affected by residual gas flow, drifting inward or outward depending on their size and density. These movements redistribute material across broad regions, shaping where different types of objects concentrate. The gravitational influence of the forming star strengthens as it gathers more mass. This deepening gravitational well pulls material inward at varying rates. Dust grains and small solids respond differently depending on their mass and composition. Icy grains from the outer regions may migrate inward until they cross a boundary where temperatures cause their surfaces to evaporate. Rocky fragments from the inner disk may attempt to drift outward but encounter regions where gas pressure creates a barrier. These exchanges contribute to the emerging structure that defines the final arrangement of material. Larger planetary embryos continue to grow by collecting surrounding material. Their gravitational influence becomes increasingly important, creating zones where smaller bodies become trapped or are forced into new orbits. These gravitational interactions may also cause embryos to migrate through the disk. A developing world moving inward or outward redistributes material around it, shaping the density and composition of the disk along its path. This migration influences where future planets stabilize and which materials they inherit. Collisions remain frequent in regions where many growing bodies exist. Some collisions produce mergers that add mass to developing planets. Others scatter fragments that contribute to dust populations. The outcomes depend on relative speeds, angles of impact, and material properties. These events help sort the disk into areas dominated by larger bodies and areas where smaller particles remain abundant. Over long periods, the system transitions from a chaotic environment into one with more defined regions. Chemical changes continue alongside these physical processes. Molecules released from evaporating ices alter the composition of gas near the forming star. Organic compounds transported from cold outer regions enrich the inner disk with chemistry that originated far beyond its boundaries. These exchanges influence the types of atmospheres that future planets may acquire. They also contribute to the diversity of surface materials present on smaller bodies such as asteroids and comets. Magnetic fields still influence charged particles within the disk. Although weaker than in earlier phases, these fields direct particle motions and help shape gas flow. Dust grains carrying slight electric charges respond to these patterns, aligning with the magnetic structure as they move. This influence affects how material settles into the midplane and how it migrates through the disk. Magnetic shaping interacts with gravitational and pressure-driven forces, creating a layered network of motions that guide travelers toward different regions. As the disk becomes increasingly organized, the paths of travelers reflect the balance between forces rather than the random flows that dominated earlier stages. Material from distant parts of the galaxy converges into new patterns. Dust grains with layered histories join developing worlds. Molecules shaped by cold clouds merge with warmer, more active environments. The system becomes a mosaic of contributions, revealing how interstellar travelers help build the diverse structures found in forming planetary systems. While natural processes guide most interstellar travelers, a small number of objects are shaped by technological activity. Spacecraft launched from the solar system represent the first human-made travelers to enter interstellar space. Their paths reflect the motions of the planets that propelled them, the gravitational assists that redirected their trajectories, and the momentum provided during launch. Once they leave the heliosphere, They drift through space much like dust grains or small fragments, influenced primarily by gravity and the faint pressure of starlight. These spacecraft carry instruments, recordings, and engineering designs created on Earth. Their construction incorporates metals, composites, and electronic components that differ from naturally occurring interstellar material. Although their presence is small compared to the mass of dust and gas in the galaxy, they introduce distinct structures into the interstellar medium. Over long periods, these objects will continue moving along their trajectories, passing between stars as silent participants in the galaxy's many flows. The forces acting on these travelers change as they move beyond the solar wind and into the interstellar environment. Within the heliosphere, they experience the influence of charged particles flowing outward from the Sun. Once they cross into interstellar space, that influence weakens. They encounter particles from distant stars and gas shaped by galactic magnetic fields. These new conditions alter the balance of forces acting on the spacecraft. Radiation pressure from nearby stars may push them slightly. Gas in the interstellar medium may exert very small drag forces. Gravity from stars and clouds may shift their trajectories over long durations. Although spacecraft lack the ability to adjust their paths after leaving the solar system, their motion remains important for understanding interstellar travel. Instruments aboard some of these missions have measured the density, temperature, and magnetic structure of the interstellar medium. These observations help reveal how natural travelers such as dust, grains, and molecules behave in similar environments. The spacecraft act not only as travelers themselves but as observers of the journey taken by material throughout the galaxy. Over time, these human-made travelers will pass near regions shaped by supernova remnants, stellar winds, or dense clouds. None of these environments will affect them strongly enough to alter their basic structure, but they may accumulate tiny impacts or chemical changes on their surfaces. Micrometeoroids may create small pits. Interaction with cosmic rays may alter the surface layers of their materials. These gradual changes resemble the processes that modify natural interstellar fragments, though the spacecraft's composition leads to unique patterns of alteration. The long-term trajectories of these objects illustrate how interstellar travel unfolds across enormous scales. A spacecraft launched from Earth may eventually pass near another star, though such encounters may occur only after millions of years. Its presence in that region would represent a small but distinct contribution from a world far away. In this way, human activity becomes part of the broader circulation of matter across the galaxy, even though the mass involved is very small compared to natural processes. These artificial travelers also offer insight into how gravity guides motion between stars. Their paths extend outward from the Sun, curving subtly under the influence of nearby stars and the galaxy as a whole. These slight shifts demonstrate the same principles that shape the motion of dust grains, comets, and larger bodies. Over time, their trajectories become part of the vast network of paths that weave throughout the Milky Way. Although their scale is minor compared to natural travelers, spacecraft represent the first steps in a long-term human presence within interstellar space. Their journeys parallel the motion of countless particles and bodies that drift across the galaxy. Together, they illustrate how contributions from many origins combine to form the complex patterns of travel found throughout the Milky Way. The galaxy contains an immense variety of travelers, each moving according to forces that act across vast scales. Dust grains drift through cold clouds, carrying layered histories of temperatures and radiation. Molecules form, break apart, and reform as they move between diffuse regions and dense environments. Comets wander between stars, preserving chemistry from distant planetary systems. Rogue planets travel in darkness, their surfaces frozen while their interiors retain traces of the worlds they once inhabited. Larger bodies within young disks gather material, shaping the early architecture of new planetary systems. Even lighter neutrinos cross the galaxy as swift messengers, revealing the processes occurring in places far beyond direct reach. All of these travelers participate in an ongoing exchange that connects one environment to another. Their paths link the diffuse medium to cloud complexes to forming stars, and forming stars to planetary systems. The cycles of movement allow material enriched by ancient generations of stars to flow into regions where new stars are born, Each journey contributes to the diversity seen throughout the Milky Way. A dust grain coated with ice may deliver molecules formed in a cold cloud to a warm region of a disk. A comet from a faraway system may pass briefly through another star's influence, sharing material shaped by environments separated by great distances. Motion across these scales is slow, steady, and patient. It unfolds over millions of years, guided by gravity, radiation, magnetic shaping, and the quiet interplay of temperature and pressure. Travelers follow paths that curve around stars, cross spiral arms, and drift through dark regions where little changes from one millennium to the next. This unhurried movement helps create the conditions from which new structures emerge. Turbulence stirs complexity into the medium. Gravity gathers material into dense regions. Cooling and heating shape chemistry into forms that enrich clouds and disks. The entire galaxy becomes a vast network where motion and transformation intertwine. The journey of matter through these processes shows how deeply connected the galaxy is. Even the material within your own body once traveled through interstellar regions, drifting across distances shaped by stars that lived and died long before the sun formed. The calcium in bones, the carbon in cells, and the oxygen in breath, each followed paths guided by the same forces that direct dust, grains, and molecules today. Their journeys extended across times far longer than any single lifespan, yet they eventually gathered into the small corner of the galaxy where Earth emerged. There is a quiet rhythm in these motions, one that mirrors the gradual settling of the mind toward rest. Just as interstellar travelers move without urgency, responding gently to the forces around them, you can allow your own thoughts to drift more slowly, softening into a state where calm comes naturally. There is no need to reach stillness quickly. A peaceful pause can arrive in the same unhurried way that dust grains, molecules, and icy fragments find their paths through the galaxy's wide and open spaces. All journeys eventually reach moments of pause, and within those pauses, new beginnings take shape. Interstellar travelers that drift through a cloud may one day become part of a star. A molecule released from warm dust may later join the chemistry of a distant region. A grain coated with ice may fall into a forming world and contribute to its early surface. These quiet transformations reveal how the galaxy renews itself through motion, connection, and time. As this story reaches its resting point, the motions that shape the Milky Way continue, carrying travelers along paths woven through light, gravity, and the deep calm of space. We, from Sleepy Stories, wish you a good night.